Hi there, this video will explain the efficiency of a DC to AC inverter with different AC loads, and we want to ascertain whether the efficiency is constant with different loads. What we've got at the moment is the inverter is switched off. Our breaker is actually off. We'll switch the breaker back on. That's switching the 6 amp breaker into the inverter on. Again, what we've got here is 13 volts and 0.5 amps. So even with no AC load, there's no AC load, the AC load, there's a clamp meter on the neutral wire here. We haven't got the AC load switched on, there's zero current on the AC side. We're still burning 13 times 0.5 amps, which is approximately 7 watts, just to run the electronics inside the inverter, even with no AC load. If we switch on the 11 watt load, we've still got 13 volts on the DC side. This clamp meter on the AC side isn't really designed for milliamps, it's more designed for amps. At 11 watts and 230 volts, we've only got approximately 50 milliamps. It's not registering on this meter. On the DC side, got 13 volts, 1.78. If we multiply those two figures to get the electrical power, voltage times current, on the DC power going in, that's 1.76 times 13, approximately 20 watts. That gives us an efficiency of 11 watts coming out, 20 going in, which gives a figure of approximately 47% efficient, which is actually quite low in terms of electrical efficiency, given that there's no moving mechanical parts. What happens if we put a bigger AC load onto it? We'll take out the 11 watts and we'll replace it with an old style 100 watt tungsten or filament bulb you now actually can't buy. Let's switch it on, let's see what happens. We've now got about 0.4 amps flowing on the AC side. This only measures 0.2. These clamp meters are not particularly accurate at very low readings. We've got 11 volts and nearly 10 amps on the DC side. 10 amps on the DC side times 11 volts going in gives us 110 watts going in. We've got 100 watts of light coming out. If we do 100 divided by 110 watts, that gives us an efficiency of 91%. So the efficiency is only high when you have quite big loads on it. This system only has a 6 amp breaker on into the inverter. So 6 amp breaker, but we've got 10 amps going in. There's going to have thermal overload very soon, so eventually the thermal components inside that circuit breaker are going to heat up and it's going to trip out, which it is designed to do. So that is deliberate. We've put quite a small rating in here so that we can evaluate our system. So the system at the moment is only spec'd up until 100 watt of loads on the AC side. So to summarize the efficiency of the inverter, AC power out divided DC power going in. On no load, the efficiency is essentially zero. We've got 7 watts dissipation just from the electronics on no load in the box. At 11 watts, we've got an efficiency of 47%, electrical efficiency through the inverter of 47%. On 100 watts, we've got an efficiency of 91%. So you only get high efficiency on inverters when you've got quite big loads on it. That's probably the highest efficiency you'll get out of it. At even bigger loads, the efficiency will start to drop with the copper I squared R losses through cables at high currents. Thank you.